Okay, last class we were talking about entropy. We've previously talked about enthalpy, and we started talking about entropy, which is the dispersal of energy, usually with units of joules per Kelvin. So thinking of things where energy is spreading out more, that's going to increase entropy. We learned a law that the change in entropy for the universe is increasing. That doesn't mean that everything is always having its entropy increase. We can decrease entropy for some things, but the overall increase in entropy, or the overall change in entropy, has to be increasing for the universe. We can freeze water. Sometimes that'll happen if you're just leaving water outside, like during the winter overnight, if we're around here. Other places it happens a lot more frequently. If you just leave liquid water out, it loses its energy to the surroundings, it freezes. And so freezing water will be spontaneous under those conditions. The magnitude of the change in entropy of the surroundings is temperature dependent. Basically, water is not going to freeze at all temperatures. And at some temperatures, water will freeze more spontaneously than at other temperatures, based on those changes in entropy. So the greater the temperature, the higher the temperature, the smaller the increase in entropy, because there's more energy around. We're increasing the temperature of our surroundings, making it hotter, there's more energy around us. So if our water is going to freeze and release energy into our environment, there's already more energy out there, and so it doesn't make as big of a difference. So adding energy to high energy surroundings causes a smaller change, a relatively smaller change. Our entropy, again, a measure of energy dispersal per unit temperature for the universe, has to be increasing. If our change in entropy for the system is decreasing, we are reducing the number of energetically equivalent states by locking our molecules into the solid form. They can't move past each other. They can't really rotate anymore. Right? We have a negative change in entropy of the system. Then our change in entropy of the surroundings is going to determine, relative to our change in entropy of the system, determines whether the change in entropy for the universe is positive or negative. So there's going to be a limit of how far we can push the change in entropy of our surroundings to keep our change in entropy of the universe positive. If we're at low temperature for our surroundings, cold environment outside, there's not as much energy around. If we're dispersing energy from our water, that's going to make a bigger impact. So we're going to have a positive and large change in entropy of the surroundings at low temperature. For high temperature, it's still going to be positive. We're still dispersing energy, but there's already so much energy around that it's not going to really make much of a difference. So looking at those two cases, if we have low temperature, we're going to have a spontaneous freezing of water. If we're at high temperature, we're going to have non-spontaneous freezing of water. In both cases, our change in entropy for the system is the same, but at low temperature, we've got a lot more energy dispersal because there's less energy around, versus at high temperature where there's more energy around, so there's less energy dispersal. The other way to think of it is, it's cold outside, the water will freeze. It's hot outside, the water won't freeze. If it's 100 degrees Fahrenheit, it's like 30 degrees Celsius outside. Those are not the same, but whatever. Water's not going to freeze. It's just going to stay being water, right? It's a non-spontaneous process that would result in a decrease in change of entropy for the universe, so it's not going to happen. Entropy has to increase for the universe. When a system exchanges heat with its surroundings, it changes the entropy of the surroundings. So exchanging heat, Q, it changes the entropy. And so if we are operating at constant pressure, like water just sitting out in a room would be at constant pressure, we can use that Q of the system, that change in heat of the system, to quantify a change in entropy for the surroundings. So we can relate these two ideas. So we've got our little fish symbol here, meaning is proportional to. So the change in entropy, the change in energy dispersal for our surroundings, the change in chaos for our surroundings, is proportional to the negative heat of the system. Negative heat of the system because our system has to lose that heat. So it's a negative value for the heat of the system to put energy into the surroundings. So for an exothermic process where we have negative heat on the system, we're going to have a positive like if we've got this red case, if X is our change in heat, if we've got a negative amount of heat, negative times negative, right, it's going to be positive. So an exothermic process is putting energy into the world. Adding energy to the surroundings. Whereas an endothermic process is going to be removing energy from surroundings or putting energy into our system or storing energy into the system, concentrating energy into the system. That's the opposite of dispersing energy. We're focusing our energy. And so we're going to have a decrease in entropy. And again, this is at constant pressure. I don't expect that we'll see non-constant pressure. The magnitude of the entropy change is also inversely proportional to the temperature. So higher temperature means smaller change in entropy of the surroundings. That's what we were talking about like 3 slides ago. And at a lower temperature, the amount of heat that is emitted from the system is going to be cause more energy dispersal, so that change in entropy of the surroundings will be higher. If we combine those two proportionalities and change it to an equal sign, we get that the change in entropy of the surroundings is equal to the negative Q of the system. So from that first proportionality, so the amount of heat that's going out into the system, or out from the system, or into the system, over temperature. So we're combining the two ideas. The more energy that, for exothermic, that's going to cause our change in entropy of the surroundings to go up. And at temperature, high temperature, we'll get a smaller change. Low temperature, we'll get a bigger change. If we're in conditions of constant pressure and temperature, we can swap out the Q with our change in enthalpy. And I think that's related to the stuff that we covered like 4 chapters ago. We're not doing volume expansion work or something to that effect. Consider the reaction between nitrogen and oxygen gas to form dinitrogen monoxide N2O. Calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. We're going to be using our brand new entropy equation. So calculate the entropy change in the surroundings associated with the reaction at 25 degrees Celsius. We are given our change in enthalpy of the reaction. So we've got that, and we can also figure out what the temperature is. We do need to plug in temperature as units of Kelvin. So 298.15 Kelvin. And for our change in enthalpy of the system, our system here is the reaction. And we're going to convert to units of joules. So shifting our decimal place over 3 to the right, 163,200 joules. We're making it negative because of the negative sign that is in the problem or in the formula. The reason that we changed it to joules was so we get units of joules per Kelvin, since that is our unit for entropy. So the entropy change is minus 547 joules per Kelvin. We also want to determine the sign of the entropy change for the system. Any ideas on how entropy is changing for our system? So I'm 85% confident. You can also just check in the book. It's the for practice 19.3. 85% positive that the sign of the entropy, well, 100% positive it's negative, and 85% sure that it's because we are decreasing the number of molecules in the system. We're going from 3 moles of molecules to 2 moles of molecules. And so we're reducing the number of energetically equivalent options that we have. Or in that equation that we looked at last class, there is this ln W term, and W is that number of ways that we can arrange the system. The other giveaway that it's negative is C, determine the sign of the entropy change for the universe. If it's not negative, if we have a positive change in entropy for the system, we don't have a number for that change in entropy for the system, so we wouldn't be able to tell if it's positive or negative. So this one is also negative. Is our reaction going to be spontaneous? does the entropy of the universe increase? It does not increase. So this one is also negative, meaning that it's not spontaneous. We would need our change in entropy of the system plus the change in entropy of the surroundings to be positive. In order for it to be spontaneous. Follow-up question. Do biological systems contradict the second law of thermodynamics? By taking energy from their surroundings and synthesizing large complex biological molecules, plants and animals tend to concentrate energy, not disperse it. How can that be possible? So if we're concentrating energy, what does that mean about our entropy? It's lower. So for our system, entropy is negative because we are concentrating energy by putting together these big biological molecules. What does the second law of thermodynamics say? It's something about the entropy of the universe. Is our rule that the entropy of the universe is increasing or decreasing? Increasing. That's our rough rule of thumb. The change in entropy for the universe is always increasing. So if our change in entropy of the system is negative, how can the change in entropy of the universe be positive? Any ideas?
Our surrounding energy is greater than our system.
Yeah, the change in entropy of the surroundings. Change in entropy of the surroundings is positive and bigger than the change in entropy of the system. So we're putting a lot of energy, concentrating a lot of energy into these biological molecules. At the same time, we're producing a lot of heat that we're dispersing out into the environment. We're burning a lot of energy to put together these biological molecules. So we're not violating the second law of thermodynamics. The change in entropy of the universe is still increasing. If we combine these two equations and multiply by negative t, we get a new equation. So just substituting in this to here, we get this This is just showing you where we're getting this. New equation that we're going to look at on the next slide. So we multiply both sides by negative t. So disperse our negative t, or distribute rather, our negative t. The t's cancel, the minuses cancel for the one with our enthalpy. So the left side turns into negative t, change in entropy of the universe, equals change in enthalpy of the system minus t change in entropy of the system. And this is really nice and convenient for one main reason. Previously, we had change in entropy, change in entropy of the surroundings. And it's a little bit inconvenient to have to figure out what's happening in the surroundings. With this new form of the equation, it's just two things related to the system and then one related to the universe. And that simplifies things nicely for us. We don't have to care about our surroundings anymore. And so if we drop the SYS subscript, we get this equation. And these are both with respect to the system. We just have to remember that. Related to this, we have this equation for Gibbs free energy, G equals H minus Ts, where H is enthalpy, T is temperature in kelvins, and S is entropy. And the change in Gibbs free energy at constant temperature, notice this H minus Ts form. If we make this a change in enthalpy and entropy, add in little triangles, this looks an awful lot like the right side of our Boxton equation there. So minus T change in entropy of this universe equals the change in Gibbs free energy. And we'll see the flipped version, I think, of that on the next slide. There it is. So the change in Gibbs free energy for a process occurring still at constant temperature and pressure is proportional to the negative of the change in entropy of the universe. This is our new favorite equation. We're throwing a lot at you. I think this one's probably more important than the last one. And this is also a criterion for spontaneity. So we can use Gibbs free energy as a way to figure out if something's going to be spontaneous. And it's sort of like chemical potential. How much chemical work we can get out of a system. Chemical systems tend towards a lower Gibbs free energy. When delta G is less than 0, so when delta G is negative, we are going to have a positive change in entropy of the universe. So like, let's say that we're doing something at 300 Kelvin and delta G is negative 50 joules. Just to put some numbers to it to show you. So negative 50 joules for our change in Gibbs free energy. And our temperature is 300 Kelvin. our change in entropy of the universe, since these both have negative signs already, our change in entropy of the universe is going to be positive. We could solve for it if we wanted to. It would be 1/6 joules per Kelvin. I don't know if that's a realistic number. It's probably not. But just showing you that if our change in Gibbs free energy is negative, our change in entropy for the universe is positive, so that's going to be spontaneous. So these are two ways that we can look at whether something's spontaneous. Gibbs free energy can be calculated solely with reference to the system because of how it's defined. It's the change in enthalpy minus the temperature times the change in entropy. So for example, on this plot, depending on where we are, this is an equilibrium reaction. So we've got nitrogen gas and hydrogen gas reacting to form ammonia, but that can also go the other way. So depending on where we are on this plot, in terms of the reaction progress, if we've got a lot of products or a lot of reactants, it's going to move spontaneously in either direction until we are at an equilibrium. Reaction occurs. When not at equilibrium, the direction is determined by Q. That's stuff that we've covered before. We've got 4 cases. We've got 2 variables. We've got 4 possible options for looking at spontaneity. Our first case is where our change in enthalpy is negative and our change in entropy is positive. So we're using our change in Gibbs free energy equation. Change in Gibbs free energy is change in enthalpy minus temperature times change in entropy. For an exothermic reaction, that's going to have a negative delta H with a positive change in entropy (2 moles to 3 moles). We've got more particles, so we've got more energetically equivalent ways of arranging those particles. The reaction is going to be spontaneous at all temperatures, since we can't have a negative temperature. So that's our first case. We've got, I believe up next is the opposite case. So for an endothermic reaction, delta H is positive with a negative change in entropy going from 3 moles to 2 moles. Delta S is negative, so we're going to have positive delta H. We're also going to have a positive term for this negative T delta S, since delta S is negative. So delta G is going to be positive at all temperatures, and when Gibbs free energy is positive, the reaction is non-spontaneous. That doesn't mean it can't happen. That just means it won't happen by itself. And then we've got two other situations where our terms end up with different signs. We have an exothermic reaction. So our delta H is negative with a negative change in entropy. So in this case, our example, we've got a restricted arrangement of molecules. We're going from a liquid to a solid. They have less freedom. They've got less ways to express their energy. The molecules do. So going from a liquid to a solid, that's going to be a negative change in entropy. This reaction will be spontaneous at low temperatures, and it's going to be non-spontaneous at high temperatures. So since delta H is negative, and delta S is also negative, we'll call that maybe Y. There's a balance between this negative term and this positive term. And if the temperature is high, then this positive term is going to be bigger than our negative term, so overall G will be positive. So our delta G will be positive. And the opposite is also true. So water freezing is a good example of this, because we know that at high temperature water doesn't freeze. At low temperature water will freeze by itself. It's spontaneous. And then our lastest and finalist case, instead of both of them being negative, we've got both of them being positive. So an endothermic reaction. We're absorbing energy from the surroundings, perhaps, and a positive change in entropy. In this case, our example is boiling water or evaporating water. So we've now changed the terms. So we've got a positive term and a negative term, and the negative term is paired up with temperature. So if temperature is really big, that's going to make the negative bigger. If temperature is really small, then our positive term is probably going to be bigger. So boiling water, a great example of this. We know that water does not boil at room temperature, where temperature is relatively low. Water doesn't boil at room temperature, but if you put a pot of water into the sun where the temperature is really high, you'll also boil your pot. And so the water, of course, is going to boil too. So at super high temperature, or in this case, not even super high, just above 100 Celsius, if you've got water in your oven, it's going to boil off. And it also happens to some extent at like room temperature. Questions about our 4 cases? Fortunately or unfortunately, this chapter is a lot of things that don't really connect well with concrete examples. So it's a little bit more physics of chemistry. And here's a table showing you all of those things with those examples. So this might be good study material if you don't want to think too hard about what's happening in a particular reaction or circumstance. So when our change in enthalpy and our change in entropy have the same sign, spontaneity depends on the temperature. It's either going to be spontaneous at high temperature or at low temperature. We can also find the temperature where spontaneity changes by setting our change in Gibbs free energy to 0 and solving for T. For all of these, if you use that equation, if you use this equation, you could come up with whether it's spontaneous or not spontaneous, or what conditions it's spontaneous or not spontaneous. You can come up with them, but you would just have to be thinking about what's the sign of the enthalpy. Is it exothermic or endothermic? And how is the entropy changing? Do we have more energetically equivalent ways of expressing the system? Do we have more ways of moving our molecules, or do we have fewer ways? So you could probably come up with the signs, and then you'd have to think through what needs to be true for it to be spontaneous. Or is it always going to be non-spontaneous or spontaneous? So this is stuff you can come up with on your own using that equation, or you can memorize the cases. That would also be valid. Let's look at doing an actual calculation with that. Hopefully this will make us feel better a little bit. So we want to calculate the change in Gibbs free energy. We're given our change in enthalpy. We're given our change in entropy. And we want to determine whether the reaction is spontaneous. Does our change in Gibbs free energy become more negative or more positive as temperature increases? So we're using our delta G equals delta H minus T delta S, and I'll give you a little bit of time, and you can work on that. All right, relatively straightforward calculation. Relatively. We're given our change in enthalpy and our change in entropy, so it's just plugging stuff in and making sure that we're using the correct units. So our change in Gibbs free energy, negative 137.5 kilojoules. However, it might be helpful to express it in joules instead. So I'm going to switch it to joules. The reason it might be helpful is because our change in entropy is joules per Kelvin rather than kilojoules per Kelvin. So 173,500 joules minus our temperature of 298.15, so that it's in Kelvin. And that's multiplied by negative 120.5 joules per Kelvin. So the negative signs will cancel out. That right term is 35927.075 joules. Combining the two terms, get negative 101,572.925 joules, and we would round that to some number of significant figures, probably 4. So 101.6 kilojoules, or negative 101.6 kilojoules. Okay, so that's our change in Gibbs free energy. Is the reaction spontaneous? What's our condition for spontaneity with Gibbs free energy? Positive or negative? Yeah, it's negative. So we have negative delta G. So this is spontaneous. It'll happen by itself. Maybe not quickly, but it will happen. When we increase temperature, we increase this 298.15 Kelvin, is that going to cause our Gibbs free energy to become more negative or more positive? More positive. So when T increases, the change in Gibbs free energy also increases, since the temperature is on our positive term. So if you increase the temperature of this reaction enough, then you would get to a point where your Gibbs free energy is 0 or positive, and then it's not going to be spontaneous anymore. Questions about that? Okay. We also can do standard change in entropy for a reaction. This is similar to our standard enthalpy change for a reaction. So for a standard enthalpy change for a reaction, it's where all our reactants and products are in their standard states. That's going to be true for our standard change in entropy of the reaction. So a reminder that this O, or 0, stands for standard. And our standard states are listed here. For a gas, it's pure gas at exactly 1 atmosphere, so we've got a defined pressure. For liquids or solids, it's also the pure substance in its most stable form at 1 atmosphere and usually 25 degrees Celsius. And for solutions, it's a concentration of 1 molar. These might be good to know. So these are things that you can throw into your brain maybe for standard states. It's pure, it's 1 atmosphere, it's 25 degrees Celsius, it's 1 molar. Obviously those don't all work together. Like if you think about it a little bit, you can't have 1 molar and also be a pure substance, but you might be able to separate out that molar, since that's a concentration, that's going to be something in a solution. Pure would be everything else. So those are some things you could try getting your brain to remember for standard states. Our standard entropy change for a reaction, like our standard enthalpy change for a reaction, is going to be our standard entropy for products minus standard entropy for the reactants. And these are molar entropies because they're like for a reaction. Entropy is a state function, so we don't care about the path that we take to get there, just the start state, the end state. But we do need to define what these standard molar entropies are. And we have to define 0 for enthalpy, because there's not an absolute value of enthalpy. For entropy, there is an absolute 0 value. So we can actually we have a solid concrete reference point, which is our third law of thermodynamics. The entropy of a perfect crystal, so perfectly repeating pattern at absolute zero, or as close as we can get to it, is 0. And the reason for that is because none of these particles at 0 Kelvin are going to be moving. They're all perfectly locked into place. And we only have one possible arrangement. So going back to Boltzmann's definition of entropy, S equals the Boltzmann constant times the natural log of W. Our number of energetically equivalent ways to arrange this is 1. They all have 0 energy or as close to 0 energy as they can, and we can't even like switch them around or anything. So we have a solid reference point for our standard entropy. Here's a look at our standard molar entropies. Entropy is an extensive property. It depends on the extent. Or the amount that we have. So if you've got a small amount, it's going to be a smaller amount. If you've got a big amount, it's going to be a bigger amount. The other type of property is an intensive property, like density. For an intensive property, if you've got a small amount, like let's think density. If I have a small amount of wood, that's going to have the same density as a big amount of wood, assuming it's the same wood. So that's intensive versus extensive. For an extensive property, a small amount, less, big amount, more. Like mass would be another extensive property. So we've got a per mole bit in here for that. At 25 degrees Celsius, one of our standard state values, the standard entropy of a substance is the energy dispersed into 1 mole of that substance. There's all sorts of things that go into our standard entropy. So it's affected by the state of the substance, whether it's solid, liquid, or gas. It depends on the molar mass. It depends on what type of a thing it is. I'll call allotrope arrangement. Of molecules / atoms. We'll see examples of, I think, all of these. It also depends on the molecular complexity, how many bonds we have, how many particles we have, or how many atoms we have. And it also depends on the extent of dissolution. So how dissolved is it versus how solid is it? So let's start looking at some of these properties. First thing to consider is the state, solid, liquid, or gas. We've talked about solid and liquid and gas before. The entropy is larger for a gas. A gas is going to have more entropy than a liquid because they're completely separated particles, and they can twist, and they can vibrate, and they can do fun waggling things with their bonds. Versus in a liquid, they can still do some of those fun waggling things with their bonds, and they can still move around relative to each other, but they can't just kind of do free rotation as much. And in a solid, they're all locked into their own particular spots. Another way to think of it as is freedom. So gases have more freedom versus liquids. Same for liquids versus solids. So just comparing across states, if we look at water, for example, water as a liquid, the standard entropy, standard molar entropy, is 70 joules per mole Kelvin. For gas, it's much higher at 188.8 joules per mole Kelvin. Molar mass also plays a factor, and we can compare, so for the previous one, for a particular compound or molecule, we could compare across the different states for that compound or molecule. With molar mass, we can compare within a family or a class of compounds that are all in the same state. If we look at the standard molar entropy for helium going all the way up to xenon, it increases as we increase molar mass. So our standard molar entropy increases with molar mass. And this has to do with the energy states that they have available to them. I don't know how helpful that is for us remembering it. So I would just say bigger molar mass. You could maybe think of it also like there's just more stuff there. So there's more things that they can be doing with their electrons maybe. And this only holds true if the substances are in the same state. We also have allotropes. So some elements exist in multiple forms. A good example of this is carbon as a diamond versus carbon as graphite versus carbon in some other state. These are also going to have different standard molar entropies just because of the number of arrangements, the way that they are put together. So for diamond has a very low standard molar entropy compared to graphite. Graphite is kind of more like in thin sheets versus diamond is more of a crystalline lattice pattern. And there's more stuff going on with carbon. You can maybe sort of see in here there's more bonds. In graphite, since they're just kind of in these flat plates, they maybe have a little bit more room to move around.
Is that why it's harder to cut through diamond? Because they're more layered on top of each other?
That could be part of it. Yeah, probably. There was an Ig Nobel Prize, I think. So if you don't know about the Ig Nobel Prizes, they're really funny. I highly recommend looking them up. It's just like people goofing around with science. So it's like, oftentimes it's like dumb discoveries or just like people were playing around and they came up with something and they're like sort of prestigious. There are a couple of people that have won Nobel Prizes and Ig Nobel Prizes, but like one of, I think it was an Ig Nobel Prize, somebody was playing around with the idea that you could take graphite and like stick it between two pieces of tape and just keep folding that, and eventually you would get down to a single atom thickness of graphite, and they showed that you could actually do that just with like Scotch tape and like pencil graphite. Basically, they could get small single atom thickness sheets of graphite from that. Anyway, so those are a fun read potentially. It's cool to see the silly stuff that people came up with. I think another one was that you could magnetically levitate frozen frogs. So there's fun stuff going on with Ig Nobel Prizes. Okay, so that's allotropes, just different forms of the same chemical. Also, molecular complexity plays a role. So increasing molecular complexity, more things that can move around. Here we're comparing argon and nitrogen monoxide. So argon, being that it's just one atom, it can move around, and that's kind of all it can do. So translational kind of like side to side, but in 3 dimensions. Whereas nitrogen monoxide also has rotational motion, and it also has vibrational motion. So that within that bond, it can vibrate, and it can also rotate around, and you can get increasingly complex forms. Basically, I would think of it as more moving parts means more entropy. So if we had something that was like 15 atoms all bonded together, that's got a lot more bonds. It's got a lot more ways that it can vibrate because of those 15 atoms and all the extra bonds and things. Another look at molecular complexity. If we've got carbon monoxide, so that's kind of like our nitrogen monoxide, we've just got 2 atoms, versus our C2H4. These have the same molar mass, but C2H4, because it has more bonds, right, within all of these bonds, there's more vibration and bond waggling and other sort of fun things that can go on within C2H4 since it's more complex, and so it's got a higher entropy. And if you increase both of them, so when molar mass and complexity both increase, you also get the entropy increasing. So NO versus NO2 versus N2O4. Adding bonds and molar mass, since both of those individually would increase your entropy, makes sense that combining them also increases entropy. And then I think this is the last one in our trend. Dissolving a crystalline solid generally increases entropy. Crystals are very structured, aqueous ions have relatively free movement. We can spread out the ions, so that's one way of dispersing the energy. They also have more ways that they can move around. They're not locked into their crystal form. They can float around and interact with more things. Okay, before we wrap up, because we're getting close to the end of time, we can also calculate standard entropy change for a reaction. And the way that we're going to do this is coefficient times standard enthalpy, that's this front term, for our products, minus the same term but for our reactants. The sigma there meaning sum. Sum up all of the terms with their respective coefficients and standard enthalpies. And we can do an example of this. So we can calculate our change in standard entropy for the reaction for this balanced equation. We are given, for each of our substances, the standard molar entropy. So sigma n times standard entropy products minus sigma n times standard entropy for reactants. That's our equation. Let's see what that looks like putting it together. So 2 times the standard entropy of H2O plus 2 times the standard entropy of SO2. That's our products, minus our reactants, 2 times the standard entropy of H2S plus 3 times the standard entropy for O2. That's for our reactants. Just showing you how it's all put together, and we'll put the numbers in now, the other numbers. So 2 times our standard entropy for H2O, 188.8. Joules per mole Kelvin. The moles will cancel out with the moles that I didn't write in for the 2. Actually, they don't cancel out. They don't cancel out. Plus 2 times the standard entropy for SO2, which is 248.2 joules per mole Kelvin, minus 2 times the standard entropy of H2S, 205.8 J per mole, plus 3 times the standard entropy for O2, that's 205.2. You wouldn't have to write it out quite as extensively as this. It's just so that it's hopefully helpful if you look back at the slides. Okay, so our left term, 874 joules per mole Kelvin. We're subtracting from that 1027.2 joules per mole Kelvin. So our change in entropy of the reaction is negative 153.2 joules per mole Kelvin. One of the nice things about this chapter is that the math isn't too difficult. The concepts are tricky, but like all of the examples that we've done, it's like the simplest formula you've ever seen in your life. This is a little less simple, but it's not too different from like calculating Q or K for like all the equilibrium stuff. Like I would say it's on a similar level to that. Questions about any of the entropy stuff we covered today? Great, we should be able to finish up this chapter, fingers crossed, on Monday.